Hi everyone, I'm Soheil and I'm here to present our work on the practicality of learning models for network telemetry. I have been collaborating with Zayd, Ram, Daniel, Reza, and Walter from University of Oregon and Niksun. The recent advances in the programmable network data planes made it possible to capture a large number of traffic features at the line rate. Availability of this vast amount of data motivates for data-driven approaches to automate different aspects of network management and security tasks. Each of these problems can be casted as a prediction or classification by machine learning models. For example, having a classification for network events. Deploying these models raises practical challenges such as training or retraining overhead. However, only a few prior studies have addressed these practical challenges. In this study, we try to explore the following practical issues in forecasting network data streams in a campus network. First, we want to see how often how the volume or selection of training data can be adjusted to reduce the training overhead without degrading the forecasting accuracy. Then, we want to see how often a model needs to be retrained in order to maintain a sufficient level of accuracy, especially when there is data drift in place. 3, we want to see how does the accuracy of forecasting models change across different segments of the data stream. And finally, we want to see whether the model type, whether it's a statistical or neural network, and the model casting, whether it's generic or per hour, affect the answers to the above questions. In order to answer the questions, we focus on two data streams. They are per second flow arrival rate. The first one, we call it RAF, which is the rate of all incoming flows to our network, to our campus network. And the second one is called RWF, which is the rate of all incoming web flows. You can see a day worth of the data for each of these data streams in the figure on the right side. And these data streams exhibit very different characteristics. We have in-depth analysis of that in our paper, and I refer you to the paper results for that. We consider 4 different models in this study. Each of these models are expected to forecast the next 5-second horizon of data, and these models are casted to show different scenarios. If we consider the plot that I have on top right side of this slide, if you consider the hour to be on the x-axis and the week to be on the y-axis, and we want to predict data on the target hour, which is showed by the red rectangle, we have different ways to cast these models. We can leverage the LGW model, which is our generic model, and is trained on prior days and prior weeks of the data, and it's used to predict any target hour. Or we can cast the data, the problem to model the LHW model, which is trained on the past hours of the target hour. Or similarly, we can use the SARIMA model that we call it SHW, that is similar to LHW and is trained on the past hours of training data, on the target data. So the last model that we can have is the LHI model, which is trained on the past instances of the target hour, which is the target hour in the same day of the week on prior weeks. We consider 6 evenly spaced target hours, 3, 7, 11, 15, 19, and 23 per day, to assess the accuracy of our models across different segments of the data stream. Comparing the accuracy of these models enables us to examine the target practical issues that we raised earlier. We used a summary distribution, essentially a box plot, to show the root mean square percentage error and to assess the accuracy of our models across 300 different randomly selected samples per target hour. We follow the best practices for tuning, for training, and testing our models. For more information, please refer to the paper. The first questions that we assess is the impact of the first question is that how does increasing the amount of training data affect the accuracy of LHW model? we realized that increasing the amount of training data for up to 24 hours improves the accuracy of forecasting for both data streams. However, further increment in the amount of training data has a diminishing return, meaning that beyond 24 hours, we do not see any measurable impact on the accuracy. The next thing is that looking at the RAF model, accuracy of models on the RAF model on top and RWF data streams on bottom, we realize that there is no variation in the accuracy of models across different target hours for RAF data stream. However, there is some variation across different target hours for the web flows, RWF. Specifically, we have higher error or lower accuracy for the night hours in RWF. We analyze the reasons or underlying reasons for this variation in RWF data streams in depth in paper. That please refer to that for more details. The next question that we answer is whether the selection of training data affect the accuracy of forecasting model. We leverage the LHI models to answer this question, that they are trained with 1, 10, and 24 prior instances of the target hour in the data stream. Here we realize that increasing the number of past instances from 1 to 10 instances improved the accuracy of our models. However, beyond 10 instances, we have again no measurable impact. The next question that we answer is that how does the recency of training data affect forecasting accuracy? For that, we use 24-hour segment of data stream and we train our model on the most recent window on 4 weeks ago and 7 weeks ago. We realize that recency of a sufficiently long training dataset has rather a minor effect on the accuracy of forecasting both data streams. Interestingly, still in this experiment, the night hours of RWF exhibit a lower forecasting accuracy. Therefore, since our 24-hour segment of each data stream provides a sufficiently rich set of variations for our data stream, they do not need to be retrained frequently, specifically in the absence of major data drift. Next question that we want to answer is that how does the selection of models affect the forecasting accuracy? In order to answer that, we have a head-to-head comparison of our different models that we have, including that we trained our LGW, the generic model, for 30 days. We trained our LHW, we passed 24 hours. LHI, we passed 24 instances. And SHW, we passed 24 hours. We realized that our LSTM models have shown similar accuracy levels across different target hours. The accuracy of our SORIMO models, however, were lower on RWF web flows during the night hours. However, SORIMO is performing as good as LSTM models for RAF data stream for all flows, and in some cases, even it was more accurate. I want to mention that there are also other analyses in the paper, for example, on the training overhead, on the longer forecasting horizons, and the short-term patterns of the error, that I would suggest that you read more about them in the paper. Therefore, the key takeaways that I can talk about is the per-hour LSTM models exhibit a higher accuracy after training only with 24 hours of the data. The accuracy of LSTM models does not depend on the recency of training data, and it means that we do not need to retrain our models frequently. Certain segments of our data streams, as you saw, are inherently more challenging to be forecasted. However, all of these LSTM models for us exhibited comparable accuracy across all different target hours. Our SORIMO models, they can have comparable or even lower accuracy than LSTM models in some cases. Before I conclude my talk, I want to bring up a limitation, which is that although our proposed methodology is generic enough that can be applied on any data stream from any network, the trained models and reported findings here are specific to our target data stream from a particular campus network. This is not a surprise, given the diverse short-term characteristics of network data streams, and given that the ML models must be customized for a specific data stream in a particular network setting, so we can ensure that we get a high accuracy. And essentially, the ML models, especially for forecasting network data streams, are not generalizable. With that, I conclude my talk, and I'm here ready for your questions. Thank you and have a great day.